To wrap up this section, I want to show an interesting example, or maybe perhaps a non-example, a counterexample. I want us to look at this vortex field. So vortex field, f is given by negative y over x squared plus y squared, x over x squared plus y squared. The reason that we call this a vortex field is because the vectors are all kind of swirling around like this in a vortex. Okay, so let's see here. I want to do the following. Quick question here is this passing? I want to take a look at this with the component test for conservative vectors fields. Does this pass the component test? This is written out for functions of 3 variables. This is a vector field and 2 variables. But all we have to do is check, does the partial derivative of this with respect to y, does this equal, question mark, the partial derivative of this with respect to x? Okay, so let's do this calculation here. If we calculate out some partial derivatives, what do we end up with? The partial derivative of this with respect to y is going to be, let's see here, it should be, we square the denominator, x squared plus y squared quantity squared, and it's x squared plus y squared times the derivative of this with respect to y is -1 minus y times the derivative of this with respect to y, which is 2y. And so we end up with x squared plus y squared quantity squared. Upstairs we have negative x squared minus y squared plus 2y squared. And so this ends up as y squared minus x squared. This partial derivative ends up as x squared plus y squared squared, x squared plus y squared times the derivative of this is 1 minus x times the derivative of this downstairs is, derivative with respect to x is 2x. And once again, if you crunch this out, we get y squared minus x squared over x squared plus y squared squared. So it looks like we just satisfied the component test. We just saw that these are going to be, the cross partial derivatives here are equal to each other. So then it looks like, our vector field should be conservative. So the integral over c of f dot dr over any closed loop needs to be 0. So what closed loop am I going to do? I'm going to do the simplest closed loop I can think of. I want to integrate over the unit circle. Okay, so unit circle, what's the parameterization? R of t is going to be cosine t comma sine t. T runs from 0 to 2 pi. Okay, this is our R of t. I know we need an R prime of t. R prime of t will be negative sine t comma cosine t. We need f of R of t. F is, remember this, f of R of t is equal to, So x squared plus y squared, those in the denominator, that's just going to be 1, because x is cosine t, y is sine t, cosine squared t plus sine squared t is 1. And so then we end up with negative y, negative sine t, and x is cosine t. Here's our f of r of t. We need f of r of t dot product r prime of t. So this dot this, negative sine t times sine t is sine squared t. Cosine t times cosine t is cosine squared t. So we get 1 here. And so at the end of the day, the integral, this is our c, the integral over c of f dot dr is equal to the integral t runs from 0 to 2 pi of 1 dt, and that's 2 pi, and 2 pi is very much not equal to 0. And so really we should be asking, what the heck is going on here? This seems to be indicating that we should be getting 0, and we're just getting 2 pi. Is something wrong here? And so the answer here is there's one little fact that I was glossing over here in all of this stuff. And so I'm showing this example to emphasize this point here. So the first thing is that there's nothing wrong here with the loop property of conservative vector fields. This theorem is true. And so if we're not getting 0 here around some closed loop, that must tell us that our vector field is not conservative. So how about the component test here? Well, we definitely have the cross partial derivatives equal to each other. We checked that there wasn't anything wrong with there. The key phrase in here has to do with this: be a vector field on an open, simply connected domain. And simply connected domain basically means that there's no holes. Okay, so let's go back to our vortex field. This is our vortex field right here. Are there holes here in our vortex field? And the answer, that marker's seen better days. The answer is yes. There's one hole. This is not defined at the origin. So in our domain here, this is defined everywhere. This is defined everywhere other than at the origin. And so when we integrate over the closed loop, this is not a simply connected domain because there's a hole in the middle, and we can't just shrink that down to a single point. So because this is, the domain here is not simply connected here, this component test doesn't apply. So just because the cross partial derivatives are equal does not mean that this vector field is conservative on the domain. So the loop property here, just because it's not conservative, so we don't have this. So there's a little, I guess, downer to end the section on, an important little fact to be aware of.